Hello, this is part 2 for the inversion formula that we did in part 1. And what's kind of neat about this little trick that we're going to do will help us get the characteristic function for a Cauchy distribution. And if you were to investigate that on your own, that's a pretty tricky equation to derive. It requires complex analysis, and anyway, I'll leave it at that. But let's jump right in. So let's let g of t be this function, this exponential function. T is over the whole real line. So let's take the Fourier transform of g of t, and it's going to create another function g of x. Now here we're kind of interchanging the g and the t from what we did before, but they're just variables. So this, usually we've called this a function and put an x, and then we created a Fourier transform which went to t, but we're inverting these, and you'll see why in the end. So the Fourier transform is take this function times the exponential function ixt. Now notice we put a little negative sign there for this Fourier transform. So that means in the inversion formula we leave that out. But so this is the Fourier transform of this function, and that should be g of t. So let's convert that to a g. And then so then we plug in g of t. And now, since this is absolute value, we're going to deal with it from the negative numbers and the positive numbers. We want this to be negative regardless of what t is. So when we're in the negatives numbers, that's negative. So this whole thing is negative. So this is correct. And then this stays the same. And when we're in the positive values for t, then we have to have that negative out front. Okay. So now to take these integrals, we combine the e, so we have a minus ix all times t, and here we would have minus, and then in parentheses, well, I'll show you, and then but I'm going to skip just take the antiderivative straight from here, and then we're integrating from these limits. Here we're integrating from these limits. You plug in 0. You get 0 in the exponent, which is 1, so you just get 1 over this. Plug in a negative infinity, this goes to 0. And then you plug in minus infinity, or infinity here, so it's minus infinity, which then makes this go to 0. Then it's minus, you plug in 0, so then the minuses cancel each other, and you get 1 over a to the ix, which is just this. Now, when you add those together, you get this, 2a squared plus x squared. So now we have our g of x function, which is a Fourier transform of g of t. So now let's use the inversion formula from the previous video, which is this. So we want to take the inverse Fourier transform of this to get our function g of t back. So we put in g of x, take the inverse Fourier transform, which on the previous video it was this, but notice that it's not negative I, and that's because we use negative I in our Fourier transform. We have to use sort of the opposite here, the complex conjugate. So now let's evaluate this. So our original function is e to the a absolute value of t. And then we plug in our g of x that we just derived, which is this. Okay, so the 2's cancel, and the e can be taken up. But let's let a equal 1 here. So that means we have e to the I absolute value of t, and here I just put it first, and then I took the pi inside, the 2's cancel, the a goes away, and that's 1. So we get this. Now here, to me, is what is so fascinating, so clever, is that if we look at a Cauchy distribution, which is this, the standard Cauchy distribution. And we just find the characteristic function for this random variable that follows a Cauchy, which is this. And by definition, it's e to the expected value of e to the itx, which is this. So we plug in this times our density, which is this. But look up here. We just derived this equals that. So that tells us the characteristic function is e to the minus absolute value of t. And try to drive that on your own. And without this little trick, it becomes pretty tough. You have to know complex analysis. And there's like a Cauchy theorem or the residual residue theorem that you have to use. It's not straightforward. So one note is if we take the first derivative of our characteristic function, which is this, it does not exist at t equals 0, which says the first moment doesn't exist of a Cauchy, and we know that. So anyway, it's consistent. And that's all I have for today. Hope you enjoyed it. I did. Please like it if you did, and subscribe so you don't miss the next one. Thanks. Bye.